Welcome everyone to our fourth Design Essentials class. Last week we talked about assemblies and found that OnShape is not as good as SolidWorks when it comes to assemblies. But we did talk about how to make part files as useful pieces in an assembly so that your bill of materials, also known as your BOM, when you make a BOM, it comes out correctly.
We're getting flagged on YouTube.
I don't know what you're talking about. Today we're going to be talking about design principles. This is probably going to be the most relevant thing to most of you. More than anything else, this is what your takeaways should be from the class. To start off, I found a do's and don'ts list for mechanical design, which then ended up being phrased as not a do's and don't list, and instead being phrased as, this is your steps you should take when you are designing something. Totally different direction that it ended up going in. I don't know why it was started as do's and don'ts, but we're going to go through each of these steps. We will talk about what you do in each of these steps, and then we'll talk about some of the more specific design considerations, such as designing for strong parts. So the first step is to clearly define your problem. Why is it important to clearly define your problem? If I told you, you need to solve world hunger, go. How do you solve that? Sure, you start looking at root causes. So the first step there is to break it down into smaller pieces. When you clearly define the problem, in school we use this engineering problem-solving format that we were forced to write out every single time, which was real tedious for homework problems, but it really was actually useful to learn, honestly. I was really upset about it when I was having to write it out every single time for every single problem, but it really stuck with me at that point, so I guess I'm kind of glad they did it. Don't tell my teachers that. The first step in that problem-solving system is to write out what is your problem. Physically write it out. In the case of a homework problem, we copied over what the homework problem was. But writing out what the homework problem is, or the problem in general that you're trying to solve, and breaking it down into the most basic ideas should be your first step. From there, you need to list out, what are you assuming? One of the assumptions that I always put there was I was assuming that gravity worked. That's an assumption. It's easy to validate the assumption. Gravity's still working. Look at that. When you list out your assumptions, you should be questioning them. You should have a reason to believe that that assumption is correct. In the case of gravity, there's a good reason. But if I'm assuming maybe I can't make whatever I'm designing more than 5 feet tall, is there actually a reason for that? Or am I just thinking that because all the previous ones have been under 5 feet tall? So you should be questioning any assumptions that you make. You should list out what might be required to solve your problem. This might be some formulas. If you are trying to calculate the speed of something, writing out how you plan on calculating that speed or what you're doing with that speed would be useful. You may need other information that you don't yet have. Maybe you're looking at the weight of something. Something that would be required is the mass of the material that you're making it out of. You may not have that on hand. Generate your solution. For us, it was actually solving the problem. But when you generate your solution, you should be generating lots of potential options, even kind of crazy ones. You'd be surprised at how often the best idea starts as a joke of, it'd be really good if we could just do this. Or someone looks at it and says, why don't you just do it this way? The more ideas that you come up with, the better it is that you might find something that works really well. And you should be able to justify your solution as to why you would want to go that way. But we'll get into that. And then you evaluate. You test, you prototype, and then you test again. And as you're going through your evaluations, you should be iterating through each of your steps. So how do you generate solutions? Well, the first principle is that no ideas are wrong ideas. Some are just better ideas. Not all ideas are equal. there should be a reason for an idea being better than the other. Maybe that reason is it's less material to make it that way. If all else is equal, you're going to go with whatever costs less to make. Maybe that reason is this is going to be way too complicated. We should do something simpler so that if it breaks, we can solve it easier or repair it easier. Oftentimes, it is better to start with something like, in the case of Queso last year when we were looking at the claw wrist mechanism, that was inspired heavily by a tractor front loader. It was Annabelle, I believe, that saw it and said, it'd be great if we could get our wrist to do something like that. Oh, Mr. Daniel. Whenever they saw it, and they said, it'd be great if we could get our wrist to do something like that. What would it take to do that? And that's a great starting point. So you look at other designs for inspiration. Another idea that was used on Queso for our launching mechanism for our drone to hold back all the force of our springs was a crossbow trigger mechanism. It ended up being probably the most simple mechanism so that all that force wasn't carried in the servo. It's best to design on paper first. When you write out something on paper, it is much easier to convey your ideas to someone who may not understand what you're saying. A lot of people are visual rather than auditory. They can't fully comprehend or imagine something 3D when you are talking about it. So being able to draw out, even in simple block shapes, your idea to convey it can help convey what you're trying to say. To be able to draw something, it would help if you took an art class. Not everyone has time for an art class. Being able to draw in perspective, a simple box, for example, being able to draw that in perspective to where it looks like a box when you're done is super useful. But I don't need to draw in 3D to be able to convey my ideas. I could talk about it looks like a box from the front, it looks like a box from the side, and it looks like a box from the top. So doing this is great, useful, not necessary. If you can just start here, it would be just as good to be able to convey your ideas. And typically, in order to design something, you really only need to practice doing straight lines and doing ellipses, which circles are ellipses, but not all ellipses are circles, just like squares and rectangles. So if I'm drawing in perspective and I want to draw a cylinder, I can draw a cylinder with an ellipses and a partial ellipses. So knowing how to draw ellipses and straight lines are all you need to be able to convey your ideas in 2D. And the next step from that is actually industrial design sketching, which is just taking this and getting really good at it and refining it. So when you look at this style that they have of, in this case, an earbud, all it is a series of ellipses. There are straight lines, some more ellipses, and you can break it down into just that. There are lots of videos on YouTube where you can learn how to do that. Your next step is to consider your costs. How do you know how much it's going to cost? You can make a bomb. If you make a bill of materials, you can then, like we talked about last week, you can then use that bill of materials to put prices to everything and make decisions on, is this too expensive? Are there other ways we can make this? In the case of FTC, sometimes you can design an alternative mechanism, or you're comparing two mechanisms, and one of them uses a stepper motor, servo, and the other uses a DC motor. And one of those costs more than the other. And if all else is equal, maybe you're going to want to go with the servo because it costs less. When you consider alternative options, you can look at alternative vendors. In this case, I pulled up a bolt from McMaster and Amazon. It is the same bolt, and Amazon is actually less expensive for a black oxide bolt, but that same bolt in zinc is less expensive for McMaster. So considering multiple sources can sometimes also save you some costs, getting multiple quotes. Buy what you can, make what you can't. It should be your mantra for everything. You should design things around the purchase parts. Why would we want to do that? Why not just build our own?
Because it would be more expensive.
It would be more expensive, but why is it more expensive?
Because of the time you spend doing it and the material you have to buy in order to do that.
That is also a really good point. So the answer was the time that you spend doing it and the mistakes you make along the way. Both of those are excellent points and both very accurate. But there's also economies of scale. It costs me a lot less. If you go to the grocery store and you're buying a 10 count of tortillas, and then right next
Of what?
to tortillas. Am I saying
Tortillas.
it? Okay. Excuse my Louisiana heritage. And then right next to it's a 50 count. And the price is different per tortilla in the 50 count than the 10 count. And it's because as you get bigger scales of material, in this case tortillas, you end up paying less per part. So the same is true for raw materials. The same is generally true for purchase parts like nuts and bolts. If I was to buy 1,000 of something, it probably cost me a lot less than buying just one of something per part. So the last bullet point here actually goes really well with what Katie said, is that do you have more time or more money? When you're designing something, sure, you may be able to buy something online that does what you need, but maybe it's going to be less expensive for you in actual money cost to take the time to design it yourself and 3D print it. So that's less money out of your pocket cost, but it takes you more time. And a lot of times you'll find in FTC you have more time than money, unless you're well-funded. And if you are well-funded, maybe that time is best spent elsewhere. So time and money are both resources that have to compete for each other's sake. Your next consideration after you've considered costs is to design around aesthetics. Aesthetics are how you make your bot look nice and pretty and get everyone else looking at it and say, that's a good looking bot. I found some tips for designing around aesthetics in particular. One of them was to design around a theme. Well, every team has a team name, so you can go around that theme, or some teams choose a theme for the year and design around that theme for that year. It helps to use a set color scheme. In this case, for the ladybug, you have black, red, and white. Most teams will have their own color scheme that they stick to themselves. And sometimes that color scheme is neon colors, which is a very broad option, but it is a theme. Use consistent design patterns. What does this mean? Any guesses?
Squiggles over here and like polka dots over here. You make either one all polka dots or all one squiggle.
That is exactly right. If you use a consistent pattern of designing, if you're using a crosshatch over here or some vertical slats over here or horizontal slats over here, if you use the same thing throughout your whole bot, it makes it look more complete. It makes it tie together more evenly. So when you're using a consistent theme, it makes it all look intentional around each other. Again, just like when you are looking at how to solve the problem, you can pull inspiration from other things. In this case, this inspiration was pulled from a ladybug. And they designed what I'm assuming is a hair blower, a hair dryer, but I don't know that for certain. This is just an image I found online. And the last thing that makes a robot, in my opinion, aesthetically pleasing is to cover the robot guts. If you cover it with plates, it makes a huge difference. If you cover all the parts that have lots of colors that contradict your color scheme or your design themes, if you cover all of those, it makes your bot more put together and look more finished. Next step is to make it modular. So you've designed your bot, you've made sure the cost is good, your mechanisms are working, your bot looks pretty. How can you make your design modular? First, why would you make your design modular? Okay, the answer was so you could change certain things out.
So you can easily take things in and out if it's broken or if you find a better way of it working.
That is correct. If something breaks, it allows you to swap it out at competition much faster if it has a modular point. But even better, if you have multiple people working on the same mechanism, maybe you're working on several different types of claws to pick up a pixel. If you all agree that this is how we're going to mount it to something like a pattern plate, then it doesn't matter what you do after that because you always know it will mount onto your bot. Fortunately for FTC, U-channels and pattern plates are common throughout everything. So if you design around that bolt pattern that you can see here, which is patented, apparently, according to GoBuilder, you can almost guarantee that you'll be able to mount it to what you're doing. And you can then swap it out. You should identify wear items after you've made things modular. Why would you want to identify wear items?
If you don't identify them before competition, almost always they will break in the middle of competition.
How many times have you been in a situation where something broke and you didn't have one? And you had to run around competition asking other teams, hey, do you have one of these that we can borrow?
Our first competition, we actually had to run around the entire competition. Our extrusion was larger by probably a 1/16 of an inch. And so we had to grind or somehow cut our extrusion down by a 1/16 of an inch. We did not have, I think we had a hacksaw. We didn't have anything to hold it in. And so we walked around. There was one team that had a vise. We tried to use their mini vise. It didn't work. So we ended up holding it between two cafeteria tables and sawing it. I think we might have accidentally cut the cafeteria table slightly, but
If you identify what your wear items are ahead of time, you can have spares ready to go. This is especially useful for 3D printed parts that are prone to breaking. But where would you identify a wear item part? How do you know what it takes to what makes a wear item part?
You work it enough times.
That's true. If it's something broke before, which is actually the last one on the list, if it's broken before and you haven't changed the design at all, it's probably going to break again. So might as well have one on spare for when that happens.
So it breaks.
That's correct. If you push your robot a lot, you'll find out what's going to break. You have to stress the system to see where it breaks.
Or if you've used it enough times to know that before you've used it, it breaks really easily, probably is
Correct. Other places are places of high stress or high loads. Maybe you've put the belt under a lot of tension, and you have to have it under a lot of tension for it to work properly, but because it's under a lot of tension, it's under high stress. If you have a lot of motion, such as a wheel, maybe the bearings might wear out, so you can plan around the bearings needing to be replaced at some point. If something sees a lot of high use, maybe it doesn't move itself, but you have parts moving past it, or it bumps into things a lot, so it's designed as like a bumper, but it gets used a bunch. Or maybe you've made it out of weaker materials, such as a 3D printed part. Then these are all things that would indicate that something would be a wear item that you should plan around and get those parts in place before you get to competition. When you design for assembly, at this point, your bot's built or your bot's designed. You've made sure that you can swap things out easily. You've made sure that it looks good. You made sure your mechanism works. You've made sure that you know what parts are going to wear. And now someone has to put your design together after you've made all the parts. When you are designing, the best thing you can do after you are done is say, okay, how would I put this together? And go through in your head, step by step, what would you do to put it together? Well, I'd put this U-channel first, and I put this, what is it called, quad block here, and I put a screw in there, and then I put the motor in, and I put the screws in for the motor. And once it's all put together, you should ask yourself, can you access those bolts? And can you access those bolts once everything's together? If you put the motor in first and then you build a whole bunch of stuff around it, can you still access the bolts for the motor to be able to take just that motor off and put it back on? And if not, is there anything you can do about that? Can you put some extra holes in the parts that you're making just so that you can get an Allen wrench in there to get to those bolts? Those access holes will save your life. How much, if you can't take it off directly, how much other stuff would you have to take off in order to access what you need? So maybe you have to take 6 or 7 things off, or maybe you can tie all 6 or 7 of those things to one plate, so where you just take the bolts for that one plate off. And it makes it a lot easier to access the bolts when you need to. Wires are another one that is hard to consider because we don't typically put wires in CAD. Not that you can't, just that it gets complicated. So when you are putting everything together and you're looking at your model and you know that you can access all the bolts, ask where the wires going to go. How are you going to run the wires so that they don't get pinched? How are you going to run the wires so that you can access where they need to plug in? You know, if you put the control hub face down, sure, it's nice and protected. How do you plug the wires in or unplug the wires? How many times have you accidentally cut a servo cable and had to replace the whole length of servo cable? Probably more times than you would like.
Is there a standard for noting in the CAD, this is where the wires will go? Or is it something that will be interpreted after?
Hold that question, and I will come back to it towards the end of this slide. The next question you should ask yourself is, can I put this on backwards? If it's intended to go one way, and I give this to someone else to put it together, are they going to be able to accidentally flip it over or put it the wrong way easily to where it looks right, but it actually doesn't work? So there's this concept, and I'm probably going to pronounce this wrong. It's originally a Japanese concept called poka-yoke, and you can see the spelling right here. And this is the concept that you can only put this together one way. You've put features in your parts to only allow it to go one way. This is why when you have plugs for your motor or for your battery, you can't put the positive to the negative because they just won't go into each other. There's only one way it can go. So in the example that they showed here is you have 2 probably power plugs that are the same size, and they fit into the holes that are the same size. It's easy to put it backwards, whereas if you make one significantly bigger than the other, it will never be able to go in backwards. When you are looking at putting something together, and sometimes it gets complicated as to how you put it together, you can throw in a couple extra features that make it a little bit easier to put things together. So on that note of the question of is there a way to note, you can potentially put some wire clips or some features that are basically like U-channels into your printed part so that you can tell whoever's assembling it, that's where you put your wires. And you can do that on a print, which we don't typically make prints for our parts. Prints being a 2D drawing, not a 3D print. But sometimes you can't put those features in. So having that conversation with whoever's putting it together is usually very handy to do, to say, hey, this is how I envision this going. And usually having that conversation before they run the wires is the better option. When you consider your wire management, not only do you need to consider where the wires are running, but you need to consider motion as well. You have big, long linear slides, and you have something moving at the end, that thing needs wires to power it. And so throwing in cable tracks and ways of cable track being run will save you a lot of headache. If you leave that for, I'll solve that problem when I get to it, it's a lot harder to find a place to fit it in. If you do it in CAD ahead of time, or at least you consider this is the area I'm leaving for that, you can often find a space to put it before everything's built. On the topic of putting something backward, it's often best to make your parts symmetric where you can. That way, if it is put in backward, it still works just fine. But if you can't, look at putting in other features. So the other example they have here for designing around assembly is you have all these little tabs that you want put in, and they've redesigned some of their parts so that all of the bolts are accessible from one side. So if I'm the assembly person and I need to access whatever this assembly is that's buried deep down, I don't have to get to it from a whole bunch of different angles. I can go from the same side every time. So after your design is done and you're looking at how am I putting this together, these are the things that you should be asking yourself is, can I access these bolts from the same side? Can I get to the bolts? How much do I have to take off whenever I'm doing this? Where are my wires going? And pretty much put yourself in the assembly person's shoes. Your next step should be to check for interferences. What are interferences? Close. It's a pretty good answer. Interferences are where things in CAD collide with each other. It's very easy in CAD to put two parts semi-overlapping each other. There's nothing stopping you from doing it. It's definitely allowed. But in the real world, it sometimes doesn't work out quite so well. So if it interferes in CAD, it's going to interfere in real life. If it doesn't interfere in CAD, sometimes it's still going to interfere in real life. It really depends on the tolerances of what you've built it to, the tolerances of your machines that you're making it on. And sometimes you have to make things close fits, and you've made them a little bit too close of a fit than what you would like. So you should have a plan in place for when that happens. If you know that these things need to be kind of tight fit together, you should have a plan for if they are too tight of a fit, what am I going to do? Am I going to redesign it with a different offset and reprint it, or maybe I take just some sandpaper to it? You can always remove material from a part. It's very hard to add material back to a part. It's a concept that we in molding called steel safe, because we made steel molds, or material safe. And it's the idea that if my part, because I'm in an invert in a mold, I can make the part bigger by removing steel, but it's hard to make the part smaller. So I always start with more material than I need, and then I can take some of that off slowly and progressively after it's done, if that's something that I need to fine tune. A lot of times we're building to tolerances that don't need to be that tight. If you tolerance things correctly, it should not interfere. Keyword there being should. I originally wrote will not interfere there, and I erased it and said should, because sometimes it will still interfere even if you did everything correctly. OnShape has an interference detection. This is actually a screenshot from that interference detection. It is apparently under the protractor measuring tools. You can run the interference detection, and it will tell you if things are overlapping. It'll give you a whole report as to what's going on there. And sometimes it'll take a long time to run if you have a lot of parts in there. It will catch any bolts that you put in there as interferences, because the way we model bolts without the threads to the biggest diameter, and the way we model a tapped hole without the threads to the smallest diameter. So there is interference clip there, but OnShape has a handy-dandy little option, which is right there, include standard content. And if you don't check that, it won't look at your bolts. That's one of the benefits of using the bolts built into the standard content rather than pulling in your own bolt files. And after you've done all of this, you go back to the problem. And you ask yourself, does this actually do what I need it to do? Have I solved this problem? Is there anything that I would change about it? Is there anything that I learned that I want to implement and do another iteration? You can ask yourself if you iterated enough, and I've put a hint there that you haven't iterated enough. If you're asking yourself if you've iterated enough, the answer is no. You want to make iterations on top of your iterations. The more iterations you do, the finer your product becomes. The more, what's the correct word for this? Finished. The more finished your final product is. When you go to your next iteration, you should ask yourself, what is good, what doesn't work, and what is meh. Solve the things that don't work, come back to the meh, keep the good. It's very important that you keep the good things. So you keep what's good, you change what's bad, you leave the meh for the next iteration when it becomes the bad. So that is the engineering process as a whole. Are there any questions on that engineering process before we move on to the next section? This is the overview of the steps needed. So just to review those once more. Clearly define the problem. Generate at least 3 solutions when you're generating solutions. You should be able to generate more than that. And sometimes they're going to be wacky ones that don't really have any foundation in reality. When we kicked off last season, we were brainstorming ideas. One of the concepts we came up with for picking up a pixel was wrapping some kind of belt around it and cinching it tight. And we actually made a prototype of that using a timing belt. And it worked out really well all the way up until you had to pick a pixel up that's against the wall. So that's the reason why it didn't stick, but it was pretty cool and it worked really well. Design it on paper first, then in CAD. Consider your price. Design for your aesthetics after your mechanism is defined. Make it modular. Identify wear items. Ensure it can be assembled. Check for interferences. Remember your manufacturing methods, which we'll get into manufacturing in a little bit, and then go back and verify number 1. Any questions on this process as a whole? Okay. Other design considerations. When you're looking at designing for something you need to be strong, or designing for something that's lightweight, or you're designing around a specific material, or you're designing around 3D printing, there are certain considerations that you should think about as you're designing. So the first one is strength. What makes a part strong? Any ideas what makes a part strong? Material is a good one. What are the other options?
The structure of it, the stability.
Okay.
Triangles.
Triangles. That actually goes really well with where I was going next. Triangles are strong. Why are triangles strong, though?
It spreads out the forces to the base more effectively than it does than a rectangle does. And because math.
The math will disagree with you about the spreading out the forces more efficiently. Because if I have a square and I put the same force here, all of that force will eventually come over here and be carried to the base the same way as if I did it to a triangle. This bottom plate will see the same.
Oh, it has, some of the forces are outward forces rather than all of them being downward forces?
No. The real reason is that because when this force moves to go straight down, it has to travel along material. And so all of that force gets put right here in this corner. And then that same force gets put in this corner, and then same right here and here. And so these corners start acting like joints. And it's easy for me to take a 4-bar mechanism that has joints here and do this, and it falls over. But I can't do that with a triangle. As soon as I do this, it stays stable. So triangle is the strongest shape. Although that's technically not fully true, circle is technically the strongest shape because it continuously transfers the force, but it's hard to make things out of circles. So generally we design around triangles, and that's why you see all these trusses designed as triangles, which, if you didn't know, these are called trusses. When they have these shapes made of all these triangles, they refer to it as a truss. And then the other answer is...
Coda knew that they were truss. He said truss in chat.
Coda knew that it was... Thank you, Coda. I appreciate it. Coda's a smart one, who's apparently cranking out bots, so I've heard. He is getting a shout out. He threw me off. The other thing that makes parts strong is the material. You can choose stronger materials than some other materials. So geometry, use triangles, not squares, but when you design parts, you want to add in radii, or fillets. Not fillets, fillets. Why do you want to add in radii? I'm getting a whole bunch of shrugs.
It distributes the forces more evenly?
No. Math. For once, math agrees with you. There's an idea called stress concentrations. So as this, and those who go to mechanical engineering school will learn a lot more about stress concentrations and what happens on a molecular level to all of the materials to make them do this. But as this force eventually moves over to go down, if it comes to a sharp corner We're going to draw this in 2D if this was a part here. So as this force moves this way, eventually it has to go down. And for that to happen, you see a lot of stress right here happening in this corner. But if you fillet it, that stress gets smoothed out. So it makes your part a lot stronger by adding fillets. This is especially true for 3D prints. So any of your 3D prints that you have straight edges on, you should try and fillet them, but you also have to consider, as we'll get into, how you're going to print it. So you don't want to necessarily fillet everything. And then you avoid poor material conditions. What does that mean? What does it mean when your material condition is poor? No.
Like really rusted and corroded metal instead of a new shiny clean one.
No, that's not what I mean when I say this here. We mean poor as in the little broken bank. No, I'm just kidding. Poor material condition is this idea that your material, if I am putting a box together and I want to put a hole here, and I get that hole really close to this edge, well, that's a upside down triangle. Really close to that edge to where this is, let's say, 0.2 millimeters. That's really thin. It's not going to take a whole lot for me to do this and break through that wall. That's a poor material condition. So if instead I change this to a full 2 millimeters instead of a 0.2 millimeters, it makes it a lot stronger, can withstand a lot more force. So when you're looking at your parts that you're about to machine or print, you should look for how close to edges or how thin your material gets, and avoid probably going less than a millimeter, definitely less than 2 where you can if you're printing parts, and if you are machining them, try and avoid the edges by as much as you can. And then materials that we typically use in FTC, you'll find a lot of aluminum, you'll find a lot of plastic of variety, you'll find wood, and you'll find steel, just to name a few. Those are pretty much the ones you're going to build your bot out of. So when we talk about poor material conditions, the best thing you can do is make your parts have as much material as possible. But that directly contradicts making parts lightweight. When you want to make a part lightweight, you want to use as little material as possible. So how do you find this balance? That's great. I'm gonna give you a bot design, and you're gonna tell me what the math is to make this the perfect amount of material, right? It's not quite so simple. So yes, you could do math. You could use a simulation software to tell you if the part is strong enough. You'll find that a lot of these parts, which these are aerospace parts, how can I tell they're aerospace parts? Any guesses? No. We use aluminum all the time for a bunch of stuff, which is what that looks like. Because they look super flimsy and like I can just take something and just break it away really easy, because they've taken away as much material as they can for the part to still function. And sometimes that's trial and error, sometimes that's simulation, but when you take away material like this, excess material, and leave behind typically a truss shape, it's called lightning pockets, and not lightning as in what strikes, but lightning as in make it lighter. So it's spelled a little differently, as you can see from lightning pockets, because you're making it lighter. You want to try and make your trusses where possible, so avoid having rectangle shapes whenever you cut away material. Try and keep it as all triangle shapes. You want to radius all corners, and this helps with machining. Why does this help with machining?
It's hard to get square corners in machining.
It is. If you're cutting something with an end mill, it is typically round. Not always, but typically for 90+% of the cases, it's going to be round. And so when I cut something with a round edge and I go to another point, it's going to leave a little curve there. And you can make that curve really small sometimes, but most times you want to do it cut fast, and so you want to use a big end mill, which means a big radius. So leave as big a radius as you can. But if you're laser cutting it, the laser doesn't care. You could put it a sharp corner if you wanted to, but it goes back to stress concentrations, and that makes it a weak part. So you should add radiuses to all of your radii, to all of your corners where you can. You want to avoid heavy materials where light materials will do. If you can make it out of aluminum and it's plenty strong enough, there's no reason to make it out of steel. If you leave it as a solid piece of aluminum and it's still too weak, maybe you move to steel, but you add lightning pockets. Maybe aluminum is too heavy, and so you move to something lighter like plastic with enough support to be able to handle the load. You should only use heavy materials where necessary. Try and lighten it, but more is a word for, it's not homogeneous. Starts with an A. For the type of material that it is. I wish I would have written this down. Anyway, effectively it means that it's a uniform material, amorphic, as opposed to, there's a crystalline, I think is the counter. But one of them means that the shape is not uniform within, like wood. Wood is known for having an amorphic grain structure. It has a stronger direction. It is not consistent. A different cut of wood will have a different strength than another one, as opposed to something like steel or aluminum, which will typically be more consistent throughout. So if you 3D print something, it will not have a consistent strength depending on the orientation. So maybe you need to move to aluminum if you can't. And then designing for lightweight, you should aim for your bot to have a low center of mass. Why would you want a low center of mass on your bot? I'm going to hear from... Okay, but why would it tip over? That's true. Some parts are heavier than others. But having a low enough center of mass so it doesn't tip over, it doesn't necessarily change anything related to it being lightweight.
Because there's too much weight on one side?
Not necessarily. The answer I'm looking for is when you have a low center of mass, it keeps your wheels engaged when you have a light bot. If you have a higher center of mass, it's easy for those wheels and the friction to make your bot pop wheelies. Even if your overall weight isn't that bad and your center of mass can still be, center of the bot. If you can have a lower center of mass, it'll keep your wheels on the ground, which will give you more speed. So you have to worry about how much weight it is when you're going lightweight to keep your motors engaged on the ground. Designing around materials. We could have an entire class just on materials with how many different types of plastics there are. So I've tried to condense it to what's relevant. With aluminum, typically you're going to cut on a machine. You can cut it by hand. You can modify it by hand, is generally better, but you will generally cut it on either a CNC machine or a laser cutter. It is lightweight, and it is stronger than plastic. You'll find a lot of aluminum being used. All of your U channels are typically aluminum. Your next material that you'll find a lot of is plastic, typically 3D printed plastic, although you can get it in sheets and you can laser cut it or cut it by hand. But plastic could be its own class by itself. There are so many different types of plastics, especially engineered plastics, but what you'll find most common are what plastics in FTC? What types of plastics? What did you say?
Am I saying it correctly? No. Dylon. The stuff that's the aluminum with the...
For plastics?
It's PVC sandwiched.
For 3D? For 3D printed plastics? Oh, I'm specifically talking about 3D printed. I guess I didn't make that clear. What was the answer? PLA and PETG are probably the two most common. There's a third one, which is ABS and TPU. So there's a bunch of them. We can make the list continue to go on and on and on, but the ones you'll find most commonly are probably going to be ABS, TPU, PETG, and PLA. Now, who knows what those acronyms stand for? That's a good guess at the P's. That is what PLA stands for. I asked what all those acronyms stood for.
I don't know any others.
So when would you use them is kind of more important than what they stand for. PLA is kind of your catch-all. PETG is another catch-all, although it is stronger. but with that strength tends to come being more brittle. TPU is flexible. You need special printers for TPU, and then ABS will typically be stronger and more flexible than PLA without so much brittleness. That's generally when you're looking for something, if you want something more flexible. You can use wood pretty easily on a robot. It's a lot easier to work with hand tools as opposed to aluminum. You can cut it with a laser or with CNC so that you can get the same level of precision. Sometimes it can be very dense compared to plastic, for example, or sometimes even aluminum. You can get a thinner aluminum piece with the same strength of wood, and that allows it to be lighter. And then there's steel. Where do you typically find steel on a bot?
Side plates.
No, side plates are normally aluminum because you want them to be lighter. You can find them as counterweights. What was your answer? That is correct, and typically you'll find them in axles. A lot of the axles that you buy, Rex shafts, will be steel so that they can withstand the torquing forces of a motor. It tends to be very heavy. You should avoid steel. There's a whole bunch of different types of steel, and you should just avoid it where you can because it's much too heavy for FTC bots for the most cases. And then there's 3D printing considerations. The first consideration is that you should add fillets everywhere you can. It gives it a lot more strength because of the stress concentrations. When you have sharp points in 3D prints and you hit it real hard, they tend to want to break right at the sharp points. You should also consider where your layer lines are going to be because it's easier for 3D prints to shear across layer lines than it is to shear perpendicular or normal to layer lines. Consider your printer's tolerances. Every printer is going to have its own tolerances. Some are much more precise than others. And there's lots of things you can find online for test prints to dial in the tolerances. You can typically adjust your printer to get better tolerances. But run some prints, measure, see where they are, and then add some extra clearance to account for the offsets that it generally is going to give you, one way or the other. There are lots of materials to choose from. You should find a couple materials, test them, and find what's best for you. Not all PLA is the same. Not all PETG is the same. Manufacturers matter. You can get one manufacturer that sells PLA and another one that says they sell the same PLA, and you'll find that one PLA is way stronger than the other. Not even close. And that's just kind of part of where it comes from. So if you find a manufacturer you like that makes good material, you should stick with them. And then plastic needs to be dry when you print it. If you are printing parts, your plastic needs to be dry. One way to dry it is what? There's a lot of ways.
Put it in an oven, or there's a filament dryer that.
Which is effectively an oven.
Yeah.
So putting it in an oven, depending on the plastic, will change the temperature. You can find what temperature you should be drying your plastic at online. I think PLA doesn't necessarily have to be dry. It might be the only exception, but pretty much any other plastic does need to be dry. The other way of doing it is you can buy some desiccant packs or silica pearl packs on Amazon, real cheap. Throw them in a Ziploc bag with your material. Typically, they'll come with desiccant packs, and seal it and let it sit there for a couple days, and it'll pull that moisture out. Why do you want the moisture out of your plastic?
Because when the moisture gets in the plastic, it creates bubbles in your material, and it doesn't create a good flow of material when
You're on the cusp of why. You're right there. Is there? Go ahead.
The water vaporizes when it's heated up by the nozzle.
That is correct. When you are melting the plastic to extrude it, you are melting it at a higher point than water. And if there is moisture in your plastic, which all plastic absorbs moisture, or almost all plastic absorbs moisture, that water gets instantly turned into steam, and that steam bursts inside your plastic, and it will give you what looks like bubbles, and it will make your final product very weak, very brittle. PETG in particular, if it is not dry, even if you don't get the issues with the printing, will be incredibly brittle. So if you find that your PETG all of a sudden is just not working as well as it used to, even though it's the same manufacturer, and you've had it for a while, maybe it's not dry. That's what I have today. Is there any questions related to design principles?
Speaking of 3D printing design principles, one thing that I've encountered while designing stuff is for one part that I've made originally for one of the clips that I had, the clips faced horizontally outwards. And when I printed it with support material, I couldn't get the support material out, so I changed it for the clips to face upwards so that I could print it better without support material there.
Correct. So orientation, again, matters for when you're printing. Whenever we look at the roadmap after next week, one of the things I plan on going into a little more is 3D printing and looking at a slicer and different orientations and why that matters. So we will touch on that a little bit more in the future. Any other questions related to the design process, related to specific considerations whenever you are designing? So just as an overview of what we've covered so far, you've looked at some mechanisms on how you could make things that mechanically function. We've looked at how to make 3D design parts and put them together in assemblies. And now we've talked about the process you should use when doing all of that. So at this point, you kind of have everything you need to be able to design a bot. So next week, we will end up talking about some electrical principles, and this will come in handy for when you're trying to troubleshoot why your bot isn't really working, even though mechanically everything functions, or at least it worked at one point. And then the week after that will be our last class. I have a hand raised. Go ahead.
Can you CNC countersunk holes?
Yes, you don't have to CNC them. So if you're laser cutting them, you cannot. The laser will not do the angles unless you have a very fancy laser. If you are putting them in an actual CNC machine, they do make bits that are countersunk, or you get it laser cut and they make bits that are tapered for a countersink that you can put in a drill and you can hand drill them yourself, which makes things with a drill press or even just a hand electric drill. You have to be careful you don't go too far because you're using your level of precision, so be careful with that, but also be aware that metric bolts and standard bolts have different angles for flathead screws. Metric bolts are typically 100 degrees and standard bolts are typically 82 degrees. So when you buy your countersink, make sure it has the right angle. Other questions? I'm not getting any online. 2 weeks from now, we'll look at 3D printing, particularly setting up parts in a slicer, so you kind of understand what some of the parameters and options you have are. We'll talk a little bit about game strategy, and I kind of touched on concept sketching today. So I will send out a message in Slack to see if there's any other topics that people want covered that we have not covered already. And I am open to anything that people feel they have not understood, want to cover more on, or maybe something we haven't touched on at all. And with that, I think we're done for today.